I think we can start, sir.
Okay. Good morning. Welcome you all to this webinar on electronics and computer engineering. Myself, J.L. Bhattacharya, and my colleague, Professor Bharghava Rajaram, we welcome you, and we are here to present you the webinar that will give you the details, that will give you the outline of this new the new program that we are introducing this year in our college, Mahendra Cole Central. Okay, so let us go to the next slide. I'll start with the objective. So the objective of this program is to create engineers who are capable of solving real world problems. That means we are making engineers, we are going to make you capable of solving real world problems, in the sense that you will be ready to join an industry. That is the industry readiness we will be providing you, and you will be equipped with techniques to solve the computational, communication, and the control oriented thing in this. You will have the background of that, but let me give you a little more of what I mean by the electronics and computer engineering. So there are these two aspects, the electronics and computer engineering. The electronics part, like you imagine that there is a car and there is a driver on that. So the car part, the hardware part is the electronics, which provides which does the whole work. That is the car does the whole work, but the driver, he sits there and he drives the car. So he's like he provides the software, because he is able to see and he is able to drive the car. He has the capability to see and drive the car around. But what we are trying to do in this whole course, that we take some aspect of the driver and put it in the car itself. So make the car more capable of driving it by itself. So there can be some 2-3 types of that. Suppose the driver is present, but there are features that he is the car tells the driver, communicates to the driver, but the control is with the driver always. But then there are types of cars where the driver is not at all needed. That means the driver is just like a passenger. He can override at any time, but he's just like a passenger and the car drives by itself. So there are different stages of the interplay between the electronics and communication, and we are going to make you prepared so that you are able to handle the different stages of this electronics and communication. Because after all, what is a driver? Driver is a kind of software, and that software is designed by an engineer. So that engineer is you. We will be making you capable of programming the hardware in such a way that it can drive by itself. So the details of that, my colleague Bhargav will tell you in the next few slides. Bhargav, please go ahead.
Yes, sir. Yes. So as Professor JLB was stating, so imagine Formula One, where you have high performance cars, and also it's at the peak of driving. So you have racers who want to leverage their hardware the most, and on the other side you have cars which want to perform the most. So a traditional hardware designer will make a car where you don't know who the driver is going to be, right? So it keeps changing, and the racer can change their which car they are racing in the middle of a season. So imagine where you build a car, or the racer himself or herself can build their own car. So you have end-to-end knowledge of both the building of a computer system and its application. And what that leads to is the design of an optimal machine to solve any problem that you have. So Professor JLB actually put it very well in the car aspect. So going forward, taking that forward into applications of such scenarios. So when you see the names of these applications, it'll be well evident where the scope is going to be, where the future of electronics and computers are going to be. So one area is an autonomous vehicle. So there's a lot of buzz on autonomous vehicles with Tesla and a lot of other companies manufacturing autonomous vehicles. So what does it take to manufacture an autonomous vehicle? It is not just the software that runs on top. It is not only the sensor. Even before autonomy was there, it was filled with sensors. It was filled with sensors for obstacle detection, sensors for your braking systems, for your cruise control. There are different levels of intelligence that a car was imbued with. But all of this is now integrated to make a car which runs on its own, which means you need sensory interfaces, you need to acquire data, you need to acquire a lot of data, and you need to process this data in the most optimal fashion. And all of this has to happen on the car. So you need an optimal machine which spans over electronics and computer science in order to build something like this. So speaking of machine learning, because that is another major buzzword in today's world. So in machine learning, when you want to implement something, say as an autonomous car, you need a lot of computation. What you would have heard from a lot of AI lectures and ML and deep learning lectures is that all of this computation takes time. You have a lot of data that you want to process, and all this data is one, it is decentralized all over the world. You have to keep collecting data, and then you need supercomputers. For example, we have a high-end supercomputer, a DGX1 computer in our lab. So we use that for a lot of our deep learning applications. So you need high amount of power to run these computers as well. But when you look at the hardware aspect of it, you have things like your application specific integrated circuits, which can be designed to run just one neural network in a very efficient fashion. Or you have field programmable gate arrays, which are hardware programmable, not just software programmable like processors or graphics processors, but hardware programmable. So you have the most optimal implementation of machine learning and deep learning algorithms when it comes to electronics and computer engineering. How best can any algorithm be implemented? Most computer engineers, while that course has its own place where you need to know all the algorithms and how it plays out in solving different applications, the way it is implemented and how optimally it can serve a particular purpose in terms of power, in terms of performance. As I told you, you have to fit deep learning into a car. You have to read from Tesla reads from 6 different cameras and does machine learning on the fly. So you need to put all of this processing power in a car. So you can't do it with traditional processors. You will be augmenting it with application specific integrated circuits, with FPGAs. So this is a very, very major application that we are looking at. And as you know, going forward, the whole world is going towards AI, ML, and deep learning. So finding proper implementations of this is a very important way forward. Again, another area where this machine learning is used. So I'll talk about one more very major application area, which is also a buzzword in today's world: Internet of Things. So if you look at this whole picture of how the flow of Internet of Things happens, again, you need sensors to collect a lot of data. These sensors can be actually physical sensors like temperature, pressure, acceleration, so on and so forth. Can be images, can also be data on the internet. Even those are sort of artificial sensors, so to speak. You have to collect all of these sensor data. You need to understand how to process. You need to know how to store this data, and then how to process this data on the cloud. So all of this, so internet is everywhere. So the whole idea of Internet of Things is it can be on anything, and it is on the internet, which means anything that we have so far can now be imbued with the capability for it to be smart. And on the other hand, you have the internet, which is pervasive. It is everywhere, which means you can collect data from anywhere. You have unlimited compute power online. You should know how to leverage this to implement an end-to-end system with Internet of Things. And Internet of Things is not just changing the way we monitor and we implement products, it is also changing the way that industries function. So Industry 4.0, so Professor JLB is a industry person. He was working in BHEL for a very long time as a senior researcher. So he will explain to you how the industry has evolved with the advent of Internet of Things. So over to you.
Yeah. So let me explain to you how the industries have evolved over the past, take the past century. So the industry started with the very basic steam engines and the machines where the power was straight from the mechanical. So the steam, let us say we burn the coal and the energy is then harnessed, and from there we utilize directly into the machines. That was the first generation. Afterwards came the mass manufacturing, in which we needed many number of products. So there the mass manufacturing industries came in the next stage, where also the electrical energy as well, because the harnessed energy is mechanical. From that we generate electrical energy, and the electrical energy can be then utilized in different forms. And this is one, that is the industry where we use number of products, where we make number of products as mass manufacturing, so that we make the products cheaper and much more available to the customers. So that is the second stage of industry. And then comes the third stage of industry, where we use robots or the numerical controlled machines to make machines. So numerically controlled machines, they make the products, and the advantage of numerically controlled machines and robot is that they are very precise, and the quality of products will be very good, because in mass manufacturing the human beings are controlling machine. In the second stage comes the numerically controlled machines, where the control part is embedded, it is inside the machine itself, and there is an overall supervision by the human being, but the machines are able to do some amount of control, not the very overall type of control. But comes to the last stage, there's the fourth generation, in which the machines are then controlled by an overall system of control, that is just like the internet. We have the IoTs, and embedded systems which are there in each machines. So these robots and these numerically controlled machines, they are then networked together, and they can then, there is a overall supervision given by the human beings, but the machines can do the whole work by themselves. So that is the fourth generation of machines. That means the robots, where it is provided with a lot of intelligence, and that intelligence is provided by with the help of these IoTs. IoTs, not only they have the simple type of sensors and processing power, but they have a very large capabilities, which are like they can have the edge type of technologies, where, say, I take an example of a refineries, for example. In a refinery, suppose there is some excavation, there is some oil excavation is being done deep inside the earth, and there is no human being at that point. So there are only sensors and actuators, and there is an intelligent control which is at that point itself. So at that point itself, we have a control as well as a processing power, and there is an automatic, there is an intelligence which is artificial intelligence, which can control in case of any emergency, any kind of situation which is an emergency requirement or a perspective requirement, that can be embedded in that device. And who is going to make those devices? Who is going to program those devices? It is our engineers, the engineers whom we produce, who are hired by the industry. They do this type of work. So we make you capable of programming those devices, and you are positioned in an industry which can, because you will be ready to take on. So because you are industry ready, that is why the industry will take engineers from our colleges. They have in the past taken our engineers, because this whole gamut of numerically controlled machines, they are again networked in such a way that there is a complete enterprise. There is an enterprise in the sense that suppose there is a cyber security that we are talking about. Then we have a cloud computing, because these are all happening at the same time. So we should make our engineers capable of working at each of these stages. That is, whether it is how to use the cloud. The cloud is also these days, it is not only for storing data, but it is capable of doing some amount of computing. It is not necessary that you should have the computer always at your hand. You can even have a mobile and on mobile phone, and using that phone you can control a machine. So this kind of capability is possible only when you have cloud computing, mobile computing, machine to machine talking. Again, this is one thing that I must tell you, like a machine can talk to a human being, in the same way a machine can talk to another machine. Machine to machine talking is very important these days, because there are situations where there is no human being. It is not possible to have any human being in such a environment like a refinery or a very hostile environment. So the machines can talk to each other, so that they coordinate between themselves. And this type of coordination, this type of learning, this type of thing, how it happens through the AI. This is through the AI, through the deep learning, through the machine learning, and we provide you with all those inputs, so that you are able to, when you pass out from the college, you are able to position yourself in an industry to take care of those things. Other things are also there in this. Excuse me. One of them is 3D printing. 3D printing is becoming very popular these days. That means there are many things which can be which can be manufactured using a 3D printing. Very complicated type of things can be manufactured using these 3D printers, which are very cheaper and very available kind of devices. Which these are the things which use a lot of these IoTs, and these IoTs are this Internet of Things. This is what we are going to provide you with all those things. This aspect I have just covered, but there is one thing which was left in the last slide, that is the cognitive. The cognitive. Can we go back to the previous slide, Bhargav? The last part of that is the cognitive computing. In cognitive computing, it is the behavioral aspect, the human behavioral aspect. That is what we try to teach our students. Behavioral aspects are very important these days. Why is it so? Because you should know how a human being thinks. So we teach our students how to deal with the behavioral aspects also. It requires some amount of the natural language processing. It requires some amount of artificial intelligence. It requires some deep learning, machine learning. Those aspects are also required in the cognitive computing system. And this overall things we are going to provide you with the education of all these things, so that you are ready to go into an industry and face a situation of the present day type. The present day industry is what? It's the fourth generation. Remember, the fourth generation in the industry in which the machines are capable of controlling themselves, and the human beings are there only to provide an overall control. And we go to the next slide. In the next slide, we will talk about, it is not just the single industry that we are talking about. No industry in this world can operate in a isolated manner. So the industries are all connected to each other. So it becomes a big enterprise. So in this enterprise, it is important that you connect these industries by through a supply chain. And we talk about the supply chain. When we talk about supply chain, we have these things, we have to keep in mind these things, that the items which are on the logistic part, the items when they are moving, from a manufacturer, it has to come to a retail, to a wholesaler, to a retailer, and then to a customer. So at all these stages, you have to track the equipment or the component or the consignment, how it is moving. We will provide you with, this is done through RFID. So this RFIDs and also the IoTs. This has made the whole system so much. It has made the whole system so much visible, that at any point where the consignment is and how it is moving it can be tracked through the systems of computer that we are having. We will give you the knowledge about the supply chain and the enterprise, how the enterprise functions and how the supply chains function. So this is about this thing. We go to the next slide. This next slide is in continuation with all that. See, I was talking to you about a hostile situation in the industry, but these days, unfortunately, or due to some consequences, so there are situations where human being cannot touch another infected human being. For example, this coronavirus, a human being cannot touch a human being because it's very infectious. So in such cases, it is possible to use a robot to do all the operations. Suppose you are putting a ventilator on a human being, that is possible to do using a robot. So robots have become very useful in medical sciences also. But we provide you with all the knowledge of how to program a robot, and also we tell you how to manage the sensors. Means the sensors which will give you the inputs which are going to come from the human body, how to manage those. So all these things will be these inputs will be given to our students, and our students also do projects. We send our students to do project to industry. We send our students to industry to do internship. They go abroad also, where they are given thorough knowledge of these things. So this is about the whole thing, how we are. So the synergizing of electronics and computing. Shall I talk about it, Bhargav?
Yes, sir. Yes, sir. Please carry on.
So electronics design in today's digital era should cater to specific needs of computer scientists. So this is the electronics these days is very, very important, because see, the electronics that we are going to use, it has gone in depth. Actually, we provide you with the knowledge of the basic electronics, then we go down and we have the very large scale integration. We we give the students the knowledge of very large scale integration of the electronics things, and we also we teach you about the analog type of VLSI, and also the digital, the discrete type of VLSI, and this complete knowledge of VLSI is given to our students. Then computer scientists should be aware of what's under the hood to get the better results. See, in this regard, the computer scientist should be, see, as a computer scientist, you should know what the hardware capability is, because the hardware that is there, it has certain capability, like your car. The driver should know what is the capability of the car. So the computer scientist is the person who is going to design the software. So he must know about the hardware, how the hardware functions. So all the intricate aspect of the hardware, the computer scientist should know. We tell them, we teach you about those aspects. And electronics and computer engineers should be capable of designing and utilizing the most optimal machine to solve the particular problem. See, the optimality. The optimality is very important, because it is not that you have to deliver a task. You have certain resource, some fixed resource. It is not that you consume all the resource in the very beginning and you are not able to deliver the task. You have to plan it in such a way that all the resources that you have are utilized in a particular manner, so that the task is delivered properly. So this is the type of optimization that we are going to talk about. Then we have this. We have designed this course curriculum from the scratch to address these needs. We have invited people from different parts of this country, and we have discussed about all the aspects of this course. We have discussed how this course should be taught, because this is becoming a new type of course, and I will talk to you about this honeycomb structure which we are telling which we are teaching. The top one at the top, you can see that the top honeycomb part is about the maths. So it is not just the width, it is not just the wideness of this the course, that is all IoTs and all that what we have been talking about. It is also the depth. You should know, the students should know deeper. So we will provide the students deep knowledge, the mathematics which is required, that is the calculus, the linear algebra, differential equations, all these things, probabilities, reliability aspect, all these aspects are taught to the student. There are as many as 5 courses of mathematics which you have to undergo. Then you have this electronics. Electronics is the basic electronics, and afterwards we move to the analog electronics, that is the linear integrated circuits. We teach the students about that, and then we go to the very large scale integration. How to manufacture a very large scale integrated circuit, and how to analyze them, how to design them. We have the tools to design a very large scale integrated circuit. I am not talking about a fabrication. The fabrication part of that, it takes place in big industries like Intel or Qualcomm, but we produce our engineers who will have the capability to design those. So that is more important. So the electronics takes care of that. Next thing is the computer science. The computer science aspect, it is a very central to each and everything, because the engineer should know about the complete the problem of this computing data structures, and this object oriented programming and the application design, all these things. Because if he does not have all this in-depth knowledge of these things, how can he do the programming of such a difficult situation, where the computer program and the hardware are almost like they are married together, they are joined together. So it is a very complicated situation. So they have to know all the design aspect and how to do the computer programming. Then the next part of it, it's very important. You see, although it is we have put it as humanities and sciences. So humanities is very important these days. Why? Because it is not just the engineer is working in a isolation or in an industry that used to happen, but an engineer can also go into the real world situation where he is interacting with other people and other human beings. So the behavioral aspect becomes very important. That is why humanities is very prime. So we teach our students about media. First thing, we in the very first level courses, we teach our students how to handle a camera, make a movie of a situation, the things which he has in the mind, how to bring it out, project that. Then physics and chemistry also is part of this. So we are putting all those things in this block that's at the bottom. And then we go to the electives. The electives is very important here because we don't fix everything here. We leave certain things onto the students. Students will develop their own likings and dislikes. So depending on their likes and dislikes, they will choose the electives. Professor Bhargav will tell you more about that. That is about the electives and the tracks. Tracks means a particular track of specialization. Whether you want to specialize in a basic computer science, or you want to specialize in a particular tracks, that is the software engineering, digital design, whatever it is. So those tracks are to be decided by the students themselves. So we leave it up to the student to decide those things, and then we proceed toward this is the last honeycomb structure, that is the track, and in the middle of all that is our ECE core courses. So the ECE core courses are there, which are which we are talking about, the environments, programmable devices, computing systems, architecture, and so on. So this is all about the core courses that we are going to discuss in this program. I leave it to Bhargav to talk a little more about the tracks. Let us proceed, Bhargav.
Yes, sir. So first, let's start with, again, a small recap of what Professor JLB has said. So this is not just a merger of just taking computer science courses and electronics courses and just putting them, in places. So every course, the syllabus has been designed ground up, or is being designed ground up to include both aspects of hardware and software. So students should have a very good hardware knowledge plus a good algorithmic knowledge to make use of this. So in the initial stages, you do more of mathematics, you build your fundamentals in your computers and electronics, and from there you launch into what we call as our ECE core. Also, I would like to add, as part of the humanities, we also teach students about leadership skills, team building. All of this is part, because there are humanities electives that students can take, which actually enhances their well-roundedness as an individual. And now that we have become a university, we are able to play around a bit more with these courses to provide the best content to the students. So I'll go over to these are the courses as Professor JLB had listed. I don't want to redo them, but I would like to focus on the ECE part of it, where it is the interface between the hardware and software. So programmable devices, how do you use microprocessors, which means design of microprocessors and utilization of them. Machine learning, the hardware aspects of machine learning, because neural networks was born out of electrical engineering as signal processing concepts. A lot of things in machine learning are derivative of electrical engineering concepts way back in the days. So we will learn it from that aspect, and also top down from the computing aspect of things. Computer architecture, it forms a perfect baseline between your software and hardware. So these are courses that we give a lot of importance to, so that students understand the importance of both hardware and software. So now the tracks that we have, currently we've designed 4 tracks, keeping future markets in mind. One of the tracks is going to be the data sciences track, and as you know, data science is blowing up like anything right now, and in the coming future, that is going to be one of the key job areas that you're going to get. Another area is embedded system design, so everything to do with IoT, biomedical instrumentation, cyber physical systems, autonomous cars, anywhere where hardware, specifically portable and sort of efficient hardware is required, an embedded system design engineer should step up. Digital design, because again, players like Intel, NVIDIA, where the core computing hardware for a lot of your algorithms are made, all of these places need digital design engineers with computing knowledge. So this is another track that we'll be offering students. And finally, a software engineering track, which is the core application track. So all of this is going to be used by software engineers to develop applications. So this is another track that we have in mind. So students will have to take courses within this track. So they'll have to take 3 or 4 courses within this track, and beyond that, they will be able to take electives which supports this these tracks. So the track is like, okay, I want to specialize, but the specialize is not as deep as a master's course. So you'll have to be wary of that. It is providing you with adequate specialization to target industries that you would like. For example, higher studies, right? So a lot of colleges in the world already offer electronics and computer engineering or electrical and computer engineering. If you look at the best universities in the world, MIT, Stanford, Berkeley, they have electrical and computer engineering courses and their departments. But in India, we do not follow that. We have a separate electrical engineering track, a separate computer science track. Very few universities of India have started the electronics and computer engineering track, and we are proud to say that we are one of them. And with the knowledge that we have at our college and tutelage from some of the best professors in the country, we hope to deliver a curriculum which is well-rounded, well-grounded, at the same time targets the industry and helps students achieve whatever higher education dreams they may have as well. So going over to the tracks in a bit more particular details about the tracks. So these are courses that one can take within a track. For example, if you chose a to be a digital design engineer, in that sense, you would want to do more digital system design, verification and testing of these circuits, low power design, high speed design, because these are, they're two sides of a coin. So you have if you want low power, your speed will drop down. If you want high speed, you need more power to support it. So all of this has to be a trade-off. You have to understand design concepts in all of these areas to be a good digital design engineer. Hardware, embedded design, you'll have real-time systems, electronic hardware system designs to build a product ground up, final product with the PCB design, with your doing your signal integrity for how your tracks work on a PCB, what controllers, what interfacing, what protocols to use. All of those you'll be exposed to as an embedded design engineer. Software design, how to construct a software, model it, evaluate it. So this is for a software application. And on the other side, for your data sciences, this is something that you would have heard of from several people. So these are courses that everybody else will offer, but with our expertise over the entire range of subjects, we'll be able to offer this with a bit more perspective. So there's one question on more about digital design. So today's electronics is more about digital systems than analog electronics. Analog electronics serves more for the communication aspect to form the physical design layers of your communication and to convert data between analog and digital domains, because the world around us is analog. But once you have data in digital form, you need to know how to effectively build a computing system out of it. So in one of the earlier slides, I would have shown you how you have your general purpose computers on one side and how you have your application specific integrated circuits on another side. Say you want to build a chip for a camera. You don't need this camera to be programmable. You have your Canon, so in your media project in your first semester, you will learn how to handle higher end cameras. So these cameras don't use general purpose processors. They use specific processors to do specific tasks in a very optimal fashion. So this part is what the digital design engineer should know. How to develop application specific IC. So you will learn about the entire design flow, right from your front end Verilog design, your problem specifications, Verilog or VHDL, and then go over from there into your validation, verification aspects. And from there, the physical design with the circuit, standard cell, or in an FPGA placement routing, and then redo this entire process until you get this optimality. Now, one other question that was asked is about the communication topics. Now, you will be exposed to the basic forms of communication in your first year courses in your basic electronics, because again, communication has an electronics implementation backend. Additionally, in your signals and systems course, you will learn about the several types of signals, modulation, and how these systems are present, how these systems are designed. And then you have your communication networks, which covers some basic aspects of physical layer design and then expands it into the software domain as well. Additionally, if you want to develop your skills in communication engineering, you have electives that you can take. As you'll see, we are also considering more tracks. Apart from the 4 tracks, you may have a communication engineering track as well. So we are contemplating all of this. So there is another question. I hope that answers the communication aspect. So there's one more question on what is VLSI. VLSI is very large scale. So your laptops, your processors, your cell phones, they have right now graphics processors have billions of transistors in them. We have just over 1 billion people in India. On a single small chip, you have billion transistors. So how do you design all of these to work in synergy to provide your application, to provide your solution. This is VLSI, where you need to put all of these into a small chip that that you can carry in your hands as a cell phone. Right? So that is your VLSI. There's another question on big data. So big data, if you can see the track on data sciences, you will be offered big data and analytics, deep learning, high performance machine learning. All of these are track courses for big data. I mean, for your data sciences, big data is key going to be a data for becoming a data scientist. So there is another question on what are the other universities in which they are offered. I know a couple of universities they are offered. I think Thapar University offers them. I'm not sure BIT may have offered them earlier, but these are two universities that I know of. But again, as I told you, with our expertise, we are building a ground-up course. I'm not able to tell you more about other courses because I've been involved with some of these other courses. I cannot talk about them right now, but we have built it up from the ground, taking expert advice from computer architects, from embedded system engineers, from data scientists to develop this course curriculum. That I think that answers that question. There's one more question on mechatronics. Now, I'll just go over to the next slide. This may be of more answer to you. So the application electives, this is actually where you use, if you look at these electives, these are places where the entirety of electronics and computers are being used. Mechatronics is one of them. Robotics is one of them, where you need, without electronics and computer science knowledge and with pure mechanical engineering knowledge, it is not possible for you to build intelligent systems. What is a robot? A robot is a machine with intelligence. So how do you imbue this intelligence? With computing. How do you get data to imbue this intelligence? Sensors. How do you process this data? Signal processing? Electronics. So all of this gels together in your robotics and mechatronics courses that you'll be able to pick up as electives. There's another course on what kind of companies need electronics and computer engineers. Now I showed you 4 tracks. You can choose companies which work in all of these. All your processor design, hardware design companies are in demand for electronics and computer engineers. I'll give you my own example. My bachelor's was in electronics and communication. I went on to do my master's in VLSI and embedded systems in IIIT Hyderabad, and then a PhD in Edinburgh in computer architecture. So I have traveled this entire stretch of electronics into computers. So I can tell you how much in demand such knowledge is within the industry. Also, okay, all the admission related queries, I would advise you that there has been a link that has been given by the admissions people of our college. I think it's better if you contact them. I will also redirect your questions to them so that they can answer. Yeah, so going forward, okay, one more question. Will this course be helpful in doing post-graduation abroad? Most definitely. I'll give you some statistics. A lot of our students, for example, our students have gotten admits in the best universities in the US. University of California in Los Angeles, Carnegie Mellon University, University of Southern California, Cornell University, Purdue, Columbia, Duke, University of New South Wales in Australia, TU Delft, which is called Berkeley of Europe. It's one of the best computer engineering schools in the world. All of these require your knowledge in electronics and computer engineering. A lot of their departments are electrical or electronics and computer engineering departments. These are the most sought after courses in your masters. So you are better positioned for a master's in a lot of these universities. Right? And that's regard with the online courses. I mean, okay, how is it similar to electronics and communication? In communication, we have more focus on the physical layer of communication. What are the different, the way wireless communication has, or even communication has developed from your earlier Morse code days to today's MIMO systems, with cognitive radio, software defined radio. Electronics and communication will focus more on that aspect. We focus more on the computing aspects of it with some exposure into communication, and you can do electives in this track as well. One thing is there are questions on which course is better, but all courses are good. They all have their applications. For example, we are offering a BTech in AI. At 12 o'clock, you will have another webinar on computation and mathematics. So all of these find their own place. So we have carved a niche in an overlap between computers and electronics. So that is our niche. AI will give you a different exposure, more algorithmic knowledge into AI, computation mathematics, more modeling knowledge. So there is need for all of this. So if you're not getting into one of these courses, the other one will definitely help you, because a lot of these are industry ready going forward into the future. There are more questions about the admissions. I will again pass this over to the uh, uh, admissions people. There are a couple more questions. Benefits of this course compared to computer science. Again, as I told you, computer science, you will learn more of the algorithms, more of foundational computer science, theory of computability. You'll learn a lot more of the application aspect. While that is again very much required, this will give you additional knowledge on how it works under the hood. For example, you might have done a lot of programming courses, but how many of you have thought, or even while buying a laptop, how many of you look at what is the cache that is available in your laptop processor? How much, what is the bus speed? All of these is what a hardware engineer looks at. And knowing them, you will be able to design better. How does memory work under the hood? How does virtual memory work? You will pretty much know, but there are new memory concepts coming up. Persistent RAM, where even if you turn off your system, your RAM stays. The RAM still stores. So you can shut down your system, you lose power, and the power comes back on, you turn it on, you can continue from where you left off, even with respect to memory. These are all the things a hardware engineer will know of, which you can take advantage of as an electronics and computer engineer. Now, will this help me develop an autonomous car? I offer an elective on intelligent, connected, and autonomous cars. And I can tell you this is the course primed to give you the adequate knowledge to design the entire control system of an autonomous car. And we have an electric vehicles laboratory in our college as well, where we have faculty members from electronics, computer science, mechanical, all working together to develop an autonomous vehicle. Now, curriculum year-wise, we'll be able to share it with you shortly. So it has to still go through some processes before that happens. So we'll give that to you. Is more focus given on hardware or software? We are not biased, right? You need a holistic, marriage between hardware and software. Who's better, your mother or your father? Both are good for you. You need both of them to work together to raise a good child. Right? So that is how we look at this electronics and computer engineering, is how we raise a child. So it is equal aspect, but I wouldn't say it's even equal, because it's a holistic design. It has to meld together to give you this sort of skill set for you to develop these machines. So I think a lot of courses have been offered. Is this course better for IoT as future? Most definitely. Again, that is my expertise right now. From computer architecture, I have again taken up embedded systems and IoT. So again, next semester we are offering an elective on IoT system architecture and design. Well primed to do that. Again, more course questions on data scientists, whether AI will be better. AI and data science. See, AI is the overarching body. Data sciences has more simple analytics as well. But again, to know more about AI and data science, there'll be a webinar on AI and even computation and math. They'll give you more information about that than us. I would defer you to those webinars. So again, so these are the electives that you take, coming back to the presentation track. And after this, I think there are more tracks that we are thinking of. And I think I'll pass it over to Professor Bhattacharya to talk about these tracks.
Okay, this slide talks about a different aspect. This is about the parallel algorithm, and this is about the computing again, and then FPGA based system and the hardware acceleration part that Bhargava has already talked about, how the hardware can be accelerated. And then we are also talking about this robotics, kinematics, and dynamics. There is a lab for the robotics to be taught to the students. So there is a lab for the robotics, and in that, whatever electronics is required, we take care of that. Signal processing and ADSP, that's speech processing and signal conditioning, all that aspect we are teaching to our students. Then communication theory, the theory of communication, that is the software defined radio, and for that we have a complete lab for our we have up to the fifth generation 5G communication lab is there in our college, and you will learn all about that. Also we will talk about the MIMO, and all these aspects of communication will be taught to you. And there are as many as 3 courses on communication that we teach to our students. One is on analog, one is on digital communication, and then we have the computer communicating, the network of communication. Then we have this network and high-speed network as the software defined network. We teach you about the different aspect, the different protocols that comes in that. We teach the students about that. So there is a course on that also. And then electromagnetics. Electromagnetics is a very basic course because it is required for all autonomous cars. It is required for all avionics things, because the radar and the RF things which come in that is all taught in this course. So it's a very important aspect. Microwave theory, antennas, all that aspects are taught in electromagnetics courses. So this is all in a nutshell what we are teaching, and you will have to do almost like 30 courses in this 4 years, in which we have all this different aspect of engineering, the electronics and the computer engineering. And let me, before ending, let me thank you all for being here, and for giving me a opportunity to talk to you and discuss with you. And whether we have been able to we have to answer all your questions. I'm not very sure, because there were many questions, I saw that, but we are running out of the time. So if there is something we can, I want to, in a very brief way, I will just introduce you to our department colleagues. My colleagues, see, it is in our college, in our department, we take the professors only from who have PhD degrees from abroad or from IITs. We have taken engineers from who have done PhDs abroad. We have also taken engineers from IIT, or we have taken engineers from the industry, like Intel, which is important. They are very important industry. We take engineers from there also. So our faculty is very highly knowledgeable people. They are able to teach you about this course in complete depth. And I hope when you come here, you will go very satisfied. You see, the first batch which came to our college 2014, most of them are placed, and all other students who went abroad, they even went to Cornell, and they are now going to Carnegie Mellon and very reputed industries in the world. And people have also gone to the London School of Economics and so on. So people have been our students have been also hired by very reputed industries. We make them ready for the industry. That's why the industry are ready to pay them. Even 50 lakhs rupees they will pay them, but they should be capable of delivering. So we make our students, we make our engineers capable of delivering that. We will make you industry ready in that sense. And the industry today looks for people who are ready for the industry. Then only they will grab you. So this is the situation at present. And with that, I just thank you once again, and I thank all the organizers and everybody to give us an opportunity. And if there is any more question, Bhargav, you would like to answer any more?
I think yeah, there have been questions. We've answered most of them. I think we can take them offline. We have given them our contact information as well. If there's any course-related queries about ECE, you can take it to either Professor Bhattacharya or me. But if it's admission-related, please take it to the admissions office. They are better placed to answer your queries about fees, admission policies, and structures, and so on. I would also like to remind you that at 12 o'clock, we have another webinar on BTech in computation and mathematics. So this will be handled by our H.O.D of the Mathematics Department and Computer Science Department. I hope that you attend that session as well. It will be as informative as this, I believe. So I guess we can close it now. I think, yeah. So thank you all. Thank you all for attending this webinar. We'll see you in MEC.
Thank you all. Bhargav, shall I close it? I can't hear you.